In this section, we move from code that only works in memory to code that works with real external data. This is a major step because useful programs do not just calculate values and stop. They read inputs from files, save outputs for later use, and handle mistakes safely. The second major idea in this section is reliability. Real-world data is messy, and good programs should not crash the moment something goes wrong. By the end of this section, you should learn how to read and write files, how to work with paths and file modes, and how to recognize runtime errors, and how to use try except to make programs safer. This is for you to understand. There will be some examples for you to link this to sensor data, logs, and reports, which is important because it shows that file handling is not just a programming syntax topic. It is a practical skill for working with real systems. Why file handling? This slide is to explain the basic motivation. Most real data does not live inside the code itself. It comes from outside sources, like sensors, logs, configuration files, or databases. If a program can only work with hard-coded data, it is very limited. File handling lets programs read inputs, save outputs, preserve information across runs, and support automation and sharing. This is an example. So it shows the flow from sensors generating readings to files storing raw data, to Python scripts reading and cleaning that data, and then finally to analysis such as dashboards, alerts, and KPI reports. This is to make you understand how it is important. File handling is the bridge between raw physical measurements and meaningful software outputs. Programs don't just compute. They interact with data. Programs are not isolated calculators. They interact with real data sources and real storage systems. Files are part of that interaction, acting as a link between collection, storage, and later analysis. That is why file handling matters so much in practical computing. What is a file? A file is introduced here as a named location on disk where data is stored. The important point is persistence. Unlike variables in memory, files continue to exist after the program stops running. This is to also separate text files from binary files. Text files store readable characters while binary files store raw bytes, such as images, audios, or executables. There are three common text-based file types: .txt, .csv, and .log. Text files are simple and flexible. .csv files are ideal for table-like data, and log files capture events over time. These are especially relevant in data processing and monitoring systems, where readings, summaries, and diagnostics are often stored in these formats. Why use files? So the benefits are summarized here. Files give us persistent storage, allow us to handle large datasets, and make it easier to share information between people or systems. This is especially important in analytics workflows, where results need to be exported, saved, and reused later rather than disappearing when the script ends. So here's a downside of not using files. If data only lives in variables, it disappears when the program exits. That makes analysis hard to reproduce and removes any audit trail. In an energy setting, for example, that means we would have no reliable record of usage anomalies or previous results. In contrast, files let us save data, reuse it later, and build repeatable pipelines. This is what turns a one-off script into something much more useful. Once data is stored, we can do trend analysis, reporting, and ongoing monitoring using historical information rather than only current values. This is to show you the relative and absolute paths. Our relative path depends on the current working directory, while an absolute path gives the full location from the root of the system. The key teaching point for me here is that file access depends not just on file name, but also on location. You may make mistakes here because the file exists, but Python is looking in the wrong place. Here we get the main file modes: R for read, W for write, and A for append. Also, here you can see that the binary modes like RB, WB, and AB. The key distinction is that read mode requires the file to exist, write mode overwrites content, and append mode adds to the end while preserving existing content. These mode choices affect behavior very strongly, so you need to understand them clearly. So W deletes existing content. This is an important warning for you. Opening a file in write mode does not simply add content. It actually would replace what was there before. That makes W powerful, but also dangerous. For logs and historical records, append mode is usually safer because it preserves previous information rather than wiping it out. This is a simple example. File equals open, then data.txt, then R. It opens the file in read mode and returns a file object. At this point, the file is open and ready to be used, but no content has been read yet. It is important for you to see that opening as the first step and not just the whole process. This is to highlight to you one of the most common beginner problems, using the wrong path and getting a file not found error. The issue is often not the file is missing, but that Python is searching in the wrong directory. The best practice note is useful. Keep project files in a known structure so paths are predictable. Now I will explain to you the open more conceptually, the open function. It returns a file object which acts as a handle for reading or writing. The function can take parameters such as file name, mode, and encoding. Here I'm also introducing the with statement as the preferred style because it handles opening and closing automatically. An open and close example. This is to show you the full basic sequence: open the file, read from it, and then close it. That closing step is very important. You may often focus on the reading part and forget that files should be closed when they are no longer needed. This is just for you to understand the complete life cycle of it. Why do we need that close? So here are 3 practical reasons. Closing frees system resources, flushes buffered data to disk, and avoids locked files. This is not just a style preference, it affects reliability. If files keep remaining open, programs can waste resources, lose unwritten data, or interfere with other tools that need access to the same files. The read method loads the entire file content as one string. That makes it very simple to use. But here is a warning as well that it can be memory heavy for large files. So read is fine for small reports or configurations, but not always the right choice for very large sensor logs or datasets. Here is an example of reading entire file. It demonstrates read function in action. The file is opened in read mode. All content is loaded into the variable content. Content equals file.read. Then printed as well, because print, then you're putting the content, and then with the file is closed, file.close. This is a clean example for small files, and it illustrates that what comes back from read is on one large string. Now I will introduce readLine, which reads one line at a time. The important point is that the file cursor moves forward with each call. That makes readLine useful when we want sequential processing, such as reading headers separately before moving through the rest of the data. Readlines in a bit more context. So now we see readlines, which reads all lines and stores them in a list. Each list element in one line string usually still includes the new line character. This is convenient for small files, but like read, it loads everything at once. So you should be aware of memory limitations. Now it's read lines and code inside the parentheses. So this example uses read lines and stores the result in a list called lines. It is a straightforward pattern and helps you to recognize that file contents can be loaded not only as one big string, but also as a list of strings, one per line. So now we are shifting from reading to writing. Writing files is how programs persist results, save cleaned data, and produce outputs for future use. The note about that /n is important here because files do not automatically break lines for us. If we want separate records, we must explicitly add new line characters. Now comes writing to a file. This example opens a file in write mode and writes the string hello world/n. It then closes the file. This is a good point to remind you that the W mode overwrites existing content. So this is appropriate when we want a fresh file, not when we want to preserve older entries. Now comes append. How do we append to a file? So this example uses append mode to add /n new line to the end of a file. This is a simple example, but it also will clearly show you the difference between append and write. So append will be preserving what is already there and extend the file instead of replacing it. It will write at the end of the file and create the file if it does not exist. Now let's look at that example. Here you can see we are having the /n new line, and then we are closing it. So it's showing you that the difference between append and write. Then comes the forgetting to close. So always close files. If you forget to close files, then it can leak file handles, risk partial writes, and remain locked. You need to leave the files open, but it will take the resources if it's not required. And it's not harmless. It can cause both correctness problems and system level issues. The with statement is presented here as a solution. It automatically closes the file when the block ends, even if an error occurs. This makes the code safer, shorter, and more Pythonic. It is one of the best habits you can develop early when working with files. Here is the with statement in action. So here you can see the actual syntax with open, then data text.r as file. So followed by the indented block, and inside the block, the file can be used normally. Once the block ends, Python closes it automatically. This is a preferred pattern you can remember. So the best practice is always use with statement. Using with improves safety and reliability for reading, writing, and logging. In any energy or monitoring pipelines, this kind of disciplined resource management is especially important because scripts may run often and process many files. Now introducing you to some common errors: file not found error, permission error, is a directory error, and Unicode decode error. This is useful because it teaches you that not all file failures are the same. Different error types point to different underlying problems such as bad paths, missing permissions, using a folder path as if it were a file, or using the wrong text encoding. This example, the open missing.txt, is intentionally kept very simple, so it attempts to open a file that is not there. This sets up the next slide for you, where you are going to see when the resulting would crash in practice. You can see the traceback and the specific exception message, file not found error. This is important because you need to become comfortable reading error output. The message tells us what failed, where it failed, and why it failed. Instead of fearing the traceback, they should let you learn how to use it as diagnostic information. This is to explain to you why do file errors happen: wrong path, typo in file name, file not yet created, or missing permissions. I would emphasize here that many runtime errors are not mysterious. They usually come from a small set of practical causes, and careful checking of path, file name, and access rights often solves the issue. What is an exception? An exception is introduced here as a runtime event that interrupts normal program execution. If it is not handled, the program crashes. This is the broader concept behind file errors and also behind things like conversion errors and type mismatches. You would see exceptions as signals that something went wrong during execution. Here are some exception types: value error, file not found error, and type error. The exceptions are typed. Python is not just saying something went wrong, it is telling us what kind of problem happened, which helps us respond appropriately. This is about reliability. Why handle exceptions? Exception handling prevents full crashes, gives users clear messages, and keeps systems running even when some inputs are bad. In critical systems such as any kind of monitoring or control, resilience is essential. One bad line of data should not bring down the whole application. It's a basic try except example. So the code attempts integer ABC, which would normally raise a value error, but because it is wrapped in a try block with an except, the program can catch the problem and respond instead of crashing. This is the first direct example of controlled failure handling for you. The output simply says error occurred. This shows that exception was caught successfully. The key point is that program continued into the except block instead of stopping. This is to illustrate to you the practical benefit of exception handling very clearly. Try except finally this structure. So this is to expand the structure slightly. The try block contains risky code, except handles errors, else can run on success. And finally, always runs whether there is an error or not. The finally part is especially useful for cleanup tasks such as closing resources or printing completion messages. This example opens a file inside the try, handles file not found error in the except, and prints done in the finally. Even if the file is missing, the finally block still runs. This makes finally a reliable piece for cleanup or guaranteed follow-up actions. The output shows file missing followed by done. This confirms two things. First, the error was handled instead of crashing the program, and second, the finally block executed no matter what. That is exactly the behavior you should understand from this structure. Best practice, catch specific errors. A bare except catches everything, which can hide bugs and make debugging harder. It is better to catch the specific exception types we expect, such as value error or file not found error. That makes our code safer and cleaner. The main takeaway here is reliability. Exception handling is not just for making code look nicer. It is what keeps systems dependable. When files are missing, inputs are malformed, or external conditions are imperfect. This is critical in monitoring and as well as control systems. Here is a practical task. Read numbers from a file and calculate their sum. The scenario is daily energy consumption, where each line represents a meter reading. This is a kind of a good example here because it combines file reading, looping, type conversion, and aggregation in one simple program. The mini program uses the with open code, the with open in parentheses in quotes energy.txt, and then followed by R as file to open the file safely, initializes the total to 0, loops through each line with the for line in file, and then adds it to the total plus equals with this integer and line. Then it prints the total here with a print in parentheses total. This is a compact but rich example actually because it combines safe file opening, iteration, and calculation in one clean pattern. Now let's look at the output. The output is 450. So here you can see that it's coming from adding 120, 150, and 180. This is to confirm that the program successfully read the file, converted text lines into integers, and also aggregated them. You can see how we can turn raw file data into a useful result. Now we will point out real limitations of the simple version. What if a line is blank? What if it contains an AN? What if conversion fails? The suggested extensions, skipping invalid data, adding try except, logging anomalies, and using helper functions all move the code toward real-world robustness. If you break the mini program into 3 conceptual stages, file as input source, loop as processing step, and output as result, then you can see. So this is a useful pattern for you to remember because many data processing programs follow this same structure. Also note that this pattern scales beyond tiny examples. Here are the key takeaways. Files provide persistence, file modes control access, with helps manage resources safely, and exceptions prevent crashes when things go wrong. So preview the move to libraries such as pandas and numpy, which is a natural next step for you once you understand the core file handling concepts. You have practiced reading and writing files, using correct modes, managing paths, handling common errors, and using try except finally. You also have begun to think in terms of debugging and logging, which are essential habits in real software work. Real programs must expect bad data and outages. Real systems cannot assume perfect input, files may be missing, data may be malformed, and sensors may fail. The goal of good programming is not to pretend errors will never happen, but to handle them gracefully so the system remains reliable. So create an energy.txt file with sensor readings is a simple task for you. Compute totals safely. Skip invalid lines with try except, append anomalies to log.txt, and verify the results manually. This is an excellent wrap-up for this section because it will connect syntax, safety, and the real-world thinking into one small but realistic mini exercise.